Just to repeat, I'm working at the Department of Mechanical Marine Engineering at the Western Norway University of Applied Sciences, and I'm the head of the research group Energy and Environmental Technologies. And if you want to look at what we are doing right now, you can just follow the link here. Now, getting started with some words up front, some housekeeping for the presentations. Given the huge area of this topic and given the time available, I think it's fair to say that the presentation I'm going to give today is somewhat incomplete and maybe also flawed. It's a very wide topic, and it's my personal approach to the topic. The conclusions people are making on the data, on the presentation, similar to what I made on the review on the reports that were available or are available publicly, is of course at everybody's own risk. For just upfront, if people are expecting some in-depth analysis of fuel cells and hydrogen, I'm sorry to disappoint you. So this is nothing I will get into today. The other thing, I'm not getting paid for this, not for the information I'm presenting, not for the points I'm making, and of course not for the presentation itself today. As Inge Christine mentioned, it's roughly half an hour, 25 to 30 minutes, and I hope we get there on time so that we have time for some questions. In any case, you can always write me an email with any kind of feedback. This should also work as a little hyperlink that you can send directly if you drop out on the presentation, if you can't take it anymore after 5 slides. So you can simply press on the little character ahead, and then you should be able to send me an email. And then today, a little bit taking liberty with the word of Donald Rumsfeld, I think I will try to talk about the known knowns and then some known unknowns, and keep far away from the unknown unknowns. So simply that we have a rough overview of the topic itself. So when Richard asked me, I was already looking up, and I found this online. Apologies for being in German. That Der Spiegel had a headline about the future ocean giants will be running on ammonia, and it was locked behind a paywall, so that I had to get the hard copy version, which fortunately is available in Norway as well. And there the title was changed to Monsters of Filth, and that global shipping is one of the biggest climate killers, which pretty much in the beginning set the tone for the presentation. What I would like to talk, it's somewhat related to that the published opinion is not always the public or the right opinion. If I take a look at the numbers from the EAA, that transport is roughly 25% of the global CO2 emissions. Shipping itself is again roughly 12% of the 3%. And based on an article from the BBC, the internet has a global greenhouse gas emission footprint of 4%. It's a little bit of a stretch calling it the monsters of filth from my point of view, just setting it into perspective. And finally, if we're talking about climate gas, we should always consider the reach and the impact of climate gases on a global scale. I will get back to that later, that you need to consider everything. If you want to talk about the climate, if you want to talk about options and climate measures, you need to take the entire value chain into considerations. In contrast to what you would refer to as emissions or local pollutants, what is for the big ships regulated today. And just a little heads up, of course, if you're talking about ammonia, nitrous oxide is also an issue as a very potent climate gas. So what we'll be looking at today is ammonia, a light in the black. You see here this little icon. I tried to organize the presentation that everything related to introduction, housekeeping has this item, and we take some words about the shipping industry and shipping itself. Move on to the fuel portfolio, not only talking about ammonia, but talking about some of the options. We take a look at the logistics, take a look at storage and bunkering, related to regulations and safety also. We take a look at the conversion of the use of ammonia, and then we hopefully summarize, conclude with something, or I will conclude with something. You, of course, are open to conclude with yourself, and then we can take a look whether this is a light in the black or just the fear of the dark. Based on other presentations I saw, I think it's always a good way to start off with a joke. For those who don't know that, 8 out of 10 Cats is a UK or English panel show, pretty much Family Feud after the Watershed. And they had a topic, the top cause for family arguments. The moderator introduced it, Jimmy Carr, and said, I don't understand the airport one anymore, the advent of Uber. Why do you have pick up people from the airport? And he got mocked from the other panelists for Beckett because some people need to pay taxes and have to get trained. And Jamali said that's some proper rich dude shit. Why doesn't everybody just get a private car? Or can you just pay a man to jump on his back and run there? So this is somewhat unrelated then, but taking some liberty from Stuart Lee, then we'll try to elaborate maybe in a painful matter on some of the topics, and then we land on that slide again and see where we at the end. So shipping, what is shipping actually? You have a lot of stakeholders involved in shipping. You've got the owners, you've got the financing, you've got the flag states, the shipbuilders, the engine and equipment manufacturers, and you've got your cargo route, for example, or general, your path the ship is traveling, and you've got the fuel, the energy supplier, you've got both the local energy supplier and maybe the company located at another point. So if you say shipping has to pay for its emissions, it's the question, who has to pay for it? Who would be the one that's most responsible for the emission of the ship, for the transport work it is doing? So that's not as easy as or straightforward as it might be. Some other numbers which are related to the later topics, especially about IMO. Based on the statistics, you've got over 90,000 ships in total. Average age of the ships, roughly 20 years. Some of them, I think bulk carriers, about 10 years. Other of them are much longer. There are still cruise ships, not in these times, but cruise ships coming to Bergen that were built in the 1940s. So there's a huge gap with respect to ship age and technology status. On the owner side and the operational side, a lot of it is concentrated in Asia. So if you want to make an impact, you surely need to have something that the main shipping market can relate to. And especially if you look at the flag states, if you think about the regulative part about IMO, you see that these 4 flag states, Panama, Marshall Island, Liberia, and Hong Kong, China, are always above 50, based on the 2019 numbers, 50% of the total deadweight tons. So this is important, as this has something to say for the regulation process, how amendments or laws are made at the IMO. So if you want to make a substantial change for the shipping industry, you need to consider where shipping is located, where shipping is operating, who owns the ship and who finances the ship. And on a more detailed level, you also need to know what the ship's all about. So this is pretty much a little bit older data from the beginning of the millennium, but I think it's still somewhat valid. If we talk about the big ships using the 2-stroke engine, the actual engine manufacturers are located in Asia. These are licensed builds. So there's a part of the energy transfer that has to happen for the measures or the efficiency improvements to take place. And if you take a look at from the DMV alternative fuel index side, if you take a look what has been implemented as environmental or climate technologies, you see that the largest part is scrubbers. SOx scrubbers. That is due to the regulation and the payback time and the cost difference between heavy fuel oil and MGO. And only a few ships are actually using LNG, methanol, LPG, battery operated, mainly short sea shipping, or as replacing an auxiliary genset. So this is from the technology point of view, there's not much happening so far. Only roughly 6% of the ships have some kind of technology on board dealing with environmental regulation. On the right-hand side, just if you compare it to cars, trucks, and trains, what the actual numbers, typical numbers for an ocean-going vessel are, the useful life, as we saw, 20, 30 years, maybe longer, 140,000 kilometers per year, operation roughly 5,000-6,000 hours per year, average load over 30,000 tons. So that these are quite some significant numbers and measures that need to be taken into account. So if we're taking a closer look at the ship itself, so this is a nice diagram from Baldi, his PhD thesis, really worth reading about. He's looking at energy flows. There's a chemical tanker about the ship system on board, what we're talking about, what we need to replace or optimize with respect to the main engines, typically two-stroke engines, 7-8 megawatts, some auxiliary engines, shaft generated at 3.2 megawatts. And then you see that the pure mechanical flow for propulsion purposes, but also the electricity generation for the hotel loads and the equipment that has to be used to operate the ship or to operate the purpose of the ship, unloading and stuff like that. So if you have then classical, the hydrocarbon fuel coming to the main engine, also serving the auxiliary and the boilers, and then you see where the energy is flowing. And if you want to make an impact, of course, the most or the highest share is going to the main engine, but you need also to consider the other auxiliary parts that are there to and have a purpose: steam production, electricity production on board, which has to be considered in the total view of changing the fuel or optimizing the total propulsion layout. And here, with respect to the auxiliary engines, here we've seen a replacement with batteries, especially for offshore supply vessels or maybe also fuel cells. And then the other part, you see that depending on the age of the vessel, the fuel bill is the biggest cost contributor, operational cost. This is for a 5-year-old vessel. If you're looking down the line 10, 15, 20-year-old, then it's roughly over 90%. It's only fuel bill. And this is also something you need to consider. It's a business shipping. So they are just operating the ships mainly or on average in total to be profitable. So if you change the fuel, if you change the volume density, if you change something about the installation on board, that you have less cargo space, if you have higher first cost or higher capital expensive in the first one, this all affects. So you can't separate these from the environmental measures or from the reducing of the climate profile. So here are some numbers now of CO2 emissions. This is from the EU, the monitoring, reporting, and verification of CO2 emissions status 2019, which has been published. All of the ships going into and out of the EU have to report their CO2 emissions. You can see it's a logarithmic scale. You've got the biggest one, the container ships, contributing with 50 million metric tons of CO2 per year. You've got bulk carriers, far over 10 million. So it's a lot of CO2. And I just did some simple calculations. You see some of the numbers here, what reduction potential you have if you would assume that all of these ships are operated by two-stroke engines. they would be converted to high pressure dual fuel engines with a pilot fuel of 1.5% in case of LNG, 3% LPG, 5% methanol, or 8% ammonia. These are numbers, rough numbers. The actual numbers can change, but then you would get a decrease overall by 27% for LNG, roughly 15% for LPG, 8 to 9% for methanol, and of course ammonia, the biggest reduction, as it's not a hydrocarbon-based fuel, over 90%. But if you take a look at the costs, here are just some spot prices. You see later, see the detailed graphics from the DNV AFI homepage for HFO, LNG, LPG, methanol, and ammonia at different points in time, 2013, 2016, 2020. Then only LNG, and only in 2013 and 2020, the price difference was in a favorable fashion, so that the CO2 reduction would also be economically viable and feasible. In all other cases, you would have a high or much higher operating expenses. So this is something that you need to consider, especially if you, for the ocean-going vessel, if you consider that the freight rates are also variable, so you have a variable fuel price on top of that. So this can ruin your business quite fast. So what are the actual candidates apart from ammonia? That just is a brief overview. I think I started with looking at all of the reports that have been published in 2018, 19, and 2020, 2021. I think it's roughly 30 or 50 big reports from known institutions, DNV, the OECD, the International Chamber of Shipping, UMAS has a lot of great reports. The UK have some, or have a clean maritime plan. There are much others. ABS has, Shell has some information, though there's a lot of information about the fuel. Most of them have introduced ammonia. The UMAS report, which is a little bit older, at least that one has just hydrogen or hydrogen-related fuel, not yet ammonia, but we've seen from 2018, 2019, ammonia has, in a way, emerged, has solidified its position as an alternative amongst other fuels. Still, the base case is oil, biodiesel, and LNG, or as the MDGL with this huge job they've done with the 30 scenarios, also looking at e-fuels. So we'll just take a look at some of the numbers for this fuel mix. I included hydrogen. Some of the numbers you should take with some grain of salt, that you can find a lot of different values at different outlets, different publication sites for these components, but I try to stick with the ones that are most often or most commonly used. LNG is mainly methane, LPG is mainly used the values for propane. And you see that ammonia has, depending on how you look at it, favorable or not very favorable properties compared to what is today's standard liquid fossil fuels or gaseous fossil fuels. Of course, high flash point, high auto-ignition temperature is favorable with respect to safety, but with respect to the combustion process, it's not necessarily beneficial. In addition to the heating value, I see only not taking the tank isolation and the tank installation into account, that everyone, apart from or based on diesel, everyone looks poor. They meet or has a lower volumetric heating value. Taking the tank into account, the tank installation is even worse. So you need to accommodate much larger spaces for the storage of these fuels. And in addition to the actual fuel properties, you of course also need to look at the fuel pathways, because as I introduced with the CO2 as a climate gas on a global scale, you need to look if you want to compare these fuels, you need to look from cradle to grave, from production to at least supply to the tank, how the fuel is performing on a climate or CO2 emission basis. And this overview from the Concave and JRC well to tank analysis does not include ammonia yet, but it would be somewhat similar to hydrogen, because you would also assume or the main part of ammonia is the hydrogen production. The air separation in the Haber-Bosch is not that significant compared, from an energy point of view, compared to the hydrogen production. So you see that you can end up worse with a carbon-free fuel compared to a hydrocarbon-based fuel. And something else that needs to be considered is the energy expended, or the energy return on energy invested. So how much energy you get from the fuel divided by the required energy to deliver the energy of the fuel. And everything below 1, that's here, is basically an energy sink, meaning that you have to put more energy into getting the fuel energy than you get out of the fuel. So this is also why a lot of reports see a significant increase in the power production or power need to actually green basically the industry and also shipping. For all the non-hydrocarbon fuels or the renewable production of these fuels or carbon neutral fuels, you need usually a lot more energy than you actually get out of these fuels. A typical value, I think, from Hall is 3 to 1 for the energy, or if you go 1/3, 33 and above, to make it viable for society. So if you take now a look at the logistics of the fuel or the fuel candidates that we're having right now, you see LNG. You've got a lot of facilities located all around the world. If you remember the vessel map in the beginning, where vessels are operating, you see you would have a lot of bunkering facilities all around the world, small and big ones, and also in the emission control areas around the US and in the Northern and Baltic Sea. And you have the experience of over 500 LNG carriers transporting the liquefied fuel. So this is, on a logistic point of view, something that surely works. Similar to ammonia, ammonia is also transported. Ammonia has in and export ports all over the world. So from a logistic point of view, it would work, and similar to methanol. That's also why a lot of these commodities already exist as, or carriers for these commodities already exist in large numbers. But then, of course, it's a question about the fuel prices in the end. And here you see development of the fuel prices in US dollars per ton from 2013 to 2020. And this is the values I used roughly for the calculation of the CO2 reduction potential and the cost associated with that. You see that at the bottom, LNG, ammonia are pretty much similar levels. So from pure per ton value, it's similar. But if you look at the ton MGO equivalent or at the ton based on the lower heating value, then of course it's a totally different view. So if you now take a look from where these different bunkering facilities exist already on the world to how you would do bunkering and what it would mean, or the risk or the challenges associated with the bunkering and storage of the fuel, you can look at maybe not as it was intended, but as LNG as the transition fuel for ammonia. The framework, the IGF code, and also the maritime experience related to using LNG as surely will greatly be of great help for ammonia and getting ammonia and other alternative fuels on a safe level starting ground. Ammonia itself is not as much, not as high flammability or flame and explosion risk as methane or LNG, but the major challenge, of course, it's toxic. But it's also not required cryogenic storage, so this makes it easier from the storage point of view and also from the handling point of view. And you see that the setup, the principal installation for ammonia fueled engine is very similar with bunkering, the LNG tanks, fuel preparation, very similar to what is currently used for LNGs. But of course, as it's not a part of the IGF code yet, you need to do your own risk assessment. The hazard identification, the hazard and operability study has to be carried out. It has, most important, you need to minimize the risk of ammonia leakage in general, as it's highly toxic. Surely all of you who have taken a brief look at ammonia know the immediate tables of the exposure limit for ammonia very, very low. You need also consider some kind of regulation or guidance document for atmospheric release of the ammonia during the bunkering process, during operations, start-stop procedures, during general maintenance. Equipment, protective equipment, sensors need to be available to detect any kind of leakage. You can, of course, use the double-walled installation, double-pipe wall installation that is being used for LNG. You need to check, especially material compatibility, both on all parts of the engines, but also on the exhaust. Can you still use the exhaust gas boiler, or do you need to change the material or have specifically made exhaust gas boilers? And as it's important, as the IGF code also mentioned, that has to be as safe as oil fuel installation. You need to think about redundancy of the fuel system itself, and especially of the pilot fuel and also the auxiliary engines, so that you can relate a safe operation of the vessel. So the most important part in all cases is reducing the risk of ammonia leakage and the impact of that it may have on persons around an exposure to ammonia. So now, before getting into the part of the regulation, just take a brief look at the timeline for the development of the regulations and with respect to the greenhouse gas emissions. If you see, first starting with the IPCC introduced in 1988, the Kyoto Protocol, the Paris Agreement, and again introducing the IGF code, how long it took from the first draft of the IGF code in 2004 until it was adopted and entered into force 13 years later. You remember your average vessel lifetime. So this is quite a challenge for the introduction of the technologies if you don't have the regulation ready at the time, and if you want to retrofit or renew your vessel or your fleet, that you have something you can base this renewal on. And here are some selected IMO regulations which would be applicable in this case. The IGC code, of course, if you could use ammonia, if you carry ammonia, if you could use it as fuel, but this is forbidden as it's toxic, so it's not allowed to use toxic products as fuel. So you need to change or amend it if you want to use this kind of installation, or the IGF code for low flash point fuels. As it's not included so far, you need approval by the administration, by the flag state that guarantees the safety. And as mentioned, the overall safety level has to be as high as for conventional oil-powered machinery. This has to make sure. If we now, before we move on to the use and the combustion of ammonia, you also need to remember that the engines have to be emission certified. And there's a neat little point about fuels, which are not hydrocarbon fuels, not derived from petroleum refining. Then you need to make sure that the engine does not exceed the NOx emission limits. Similar to these kind of fuels, it must not contain inorganic acid, must not jeopardize the safety of the ship or be harmful to personnel. So these regulations already set quite a damper on ammonia itself, so making not the obvious choice there.
Peter,
yeah.
Could I please ask you to wrap up in a few minutes, because you have spent half an hour already, so we should have some time for questions as well.
Yeah, I will try to get through faster now. So looking at the fuel specification, MAN has released a preliminary fuel specification for ammonia, but from a standard point of view, nothing has happened yet. Only diesel and LNG are implemented. If you take a look at the conversion process, the look back, of course, a lot of are referring to the tests that were done in Belgium in 1943. Already looking at good reasons using ammonia, good anti-knock value. This is something that you will see a lot of the time, as most of it was done on spark-ignited engines. A lot of interest it gained in the 1960s and 70s, especially in the US, from a military point of view. Nuclear fuels, using small nuclear power plants to produce ammonia and use it as fuel in spark-ignited or compression ignition engines. The general conclusion was spark-ignited are to be preferred, but you need a very high energy source. The Danish test, which tests a lot of alternative fuels, found ammonia to be the last favorable fuel, also based on their engine setup. But generally, it can be burned, it can be used, but you need to consider some stuff. So where do we go from here? Ammonia is not likely to be used in a monofuel engine. From my point of view, it will be used in a low or high pressure dual fuel engines. If you want to use it in a spark ignition engine, we will use some kind of dissociation device that generates hydrogen and use hydrogen assistance in the combustion, especially for larger engines. You need to take a look at the heat of vaporization. If you inject it as a liquid, you need to take a look also at the combustion products. You will produce a lot of water. You will have higher NOx emissions. You need SCR for sure. And of course, you need to look at nitrous oxide, as it's a heavy climate gas. So these are just some numbers calculated for some kind of engines with a different kind of bore and engine speed. The last two are two-stroke engines. And just if you take a look based on a typical flame speed, how much of the bore of the combustion chamber you can cover without hitting the border, the quenching distance, you see that ammonia, again, is separate from the hydrocarbon fuels, and it's most likely better adopted to two-stroke, large two-stroke engine. Also, if we look at the frame propagation, we take a look at the flame speed and how much time in crank anchors, in piston movement it will take to combust the fuel. Ammonia takes quite a long time to have a full combustion on the laminar flame speed. So this is something that is surely more advantage or much less of a burden for a two-stroke slow speed engine. And you need to include some kind of external kinetical energy, which you can get from a high pressure diesel injection, which is actually the concept that is proposed from MAN for their two-stroke engine. So we stick the landing now, wrapping it up. This is quite a good podcast that has been done with the now CEO of Maersk. I'm not going to butcher his last name. And he pretty much sums it up that they have two candidates, ammonia and methanol. Methanol has a very low flame point. It's a safety issue. Ammonia is toxic. It's also a safety issue. But we need to get this done right now, because if you want to think about 2050, 20 years of ship life, you need to have it done by 2030. Otherwise, you won't be using it. And the beauty of using these in a combustion engine is that you can retrofit the existing ships with that. A little callback from 2010 Congress of CIMA Congress in Bergen. There was the question, what's the future fuel? And then the answer from a Maersk representative was, the obvious answer would be still heavy fuel oil, but with some kind of emission treatment devices and some emerging patchwork of alternative fuels. So they have quite a good track record. I think that this statement still stays true today. So if we take a look at where we started, we can say that why don't everybody move to hydrogen fuel cells? And then it's, of course, because some people need to pay freight taxes, fuel bills, and have to get to all kinds of places all around the world. And because you simply can't pay or force companies to build new vessels and exchange their machinery by itself. So is ammonia the obvious choice as a fuel for ship? No, but it can be depending on some individual parameters, especially regulation, incentives, the economics and logistics, as we see from the uptake of scrubbers. So this is something to learn from. And you see here the money spent from the Norwegian NOx Fund on technology development. And then you see the rather widespread application of LNG and SCR systems was based on if you put a lot of money into it, then of course you can lift or get a technology started. So that's all for me. And sorry for taking a lot of your question time.